Hey folks, hopefully you had a chance to watch the TED Ed video and have gotten a bit about what it means for something to be an acid or a base, along with some of their characteristics. I'm just going to provide in this video a little bit more detail and some extra information about how acids and bases work. So first off, we'll start with something that you're familiar with, the pH scale. So you theoretically should have learned about this in classes before. The pH scale is how we measure how strong an acid or a base is. And it's a logarithmic scale, which means that each number that you change on the scale is actually a tenfold change. So instead of going up by 1 or even 10, you're actually multiplying by 10 each time. So on this scale, if you look at a pH of 3, that's more towards the acidic side of things, but a pH of 3 is actually 10 times more acidic than a pH of 4. And you might notice some things on here that maybe are a little bit alarming to you, that like soda is pretty acidic, tomatoes, coffee you probably knew about. But if you go to the dentist and they tell you to lay off some acidic foods for a while, the reason that they say that is because acidity tends to kind of eat away or corrode the enamel on your teeth. So that can be really bad for your teeth. So that's why they might tell you to lay off some of those foods. So acids, some of this is reiteration from the video, but acids tend to have a very low pH. So their pH is going to be less than 7 because 7 is a neutral pH. They're going to taste sour and they can actually corrode or dissolve metals. And they tend to lose a hydrogen ion in chemical reactions. So the video talked about losing a proton, and I don't want that to confuse you because we know that when an element loses a proton, it becomes a different element. So when the video is talking about losing a proton, they're basically saying losing a hydrogen ion. So remember, hydrogen only has one proton anyway, and if it's an ion, then it doesn't have any electrons. And so we can think about that hydrogen ion as just being like one proton. Of course, it would have a neutron along with that. So that is going to be given away by the acid compound. So we're dealing not with an element here with acids, we're dealing with compounds, and the compound is going to give away a hydrogen ion. So that's what the video was talking about when it was talking about giving away a proton. We can recognize acids because often when they're written out, they often start with an H at the front. So they kind of put that hydrogen ion up at the front of the name of the acid. And some examples are going to be stomach acid, vinegar, which we've used in class and we call acetic acid, and citric acid is what is found in citrus fruits. Bases are going to have a high pH, more than 7. So remember, 7 is neutral. We're going to be higher for bases. And it's going to have a bitter taste, and they're going to feel slippery. So things like soap are actually bases, and that's why soap has a slippery feel to it. Bases are going to tend to lose a hydroxide ion in a chemical reaction. So we can think about that as the whole compound losing an electron because a hydroxide ion, this OH, is going to have a negative charge overall because it's an ion, and it's a negative ion. And so when a compound loses a hydroxide ion, that is what determines that that compound is a base. And often to make things easy for us, we write the base with that hydroxide ion right on the end of it. So we'll have an OH kind of on the end of the base. So that's how we can recognize a base. Things like bleach, drain cleaner, so a lot of cleaning agents are actually bases. Windex and Tums are actually a base. And the purpose of Tums is actually to kind of balance out some of that stomach acid. If you have acid reflux, some of that stomach acid can get up into your esophagus. And if it's really bad, it can actually start to eat away at your esophagus. And so Tums kind of counteract that by being a base in that scenario. So the strength of an acid or a base is going to refer to how much that acid or base dissociates or splits apart. We can also kind of use the term dissolves in water. So a strong acid or a base, we can see in this little diagram here, a strong acid or a base is going to completely dissociate or dissolve in water. So all of our hydrogen ions are dissociated from our chlorine ions. A weak acid or a base is only going to partially dissociate. So down here we can see a weak acid, if we put it in water, you might get like a couple of the hydrogen ions dissociating, but not all of them. And also I want to point out that we should know this symbol down here is a reversible reaction symbol. So because only some of the hydrogen ions have dissociated, we can kind of move back and forth in this particular reaction and we can reach an equilibrium. Versus with a strong acid or a base, we don't have a reversible reaction. We're going to completely dissociate, and in an acid, we're going to completely split apart our hydrogen ions, and in a base would give up all of the hydroxide ions when it was put into water. Strength also, we can recognize strength based on the pH scale. So stronger acids and bases are at the end of the scale. So we can see these very low pHs are going to be strongly acidic, and the very high pHs are going to be strongly basic. We also use the term alkali for basic things. And the weaker ones are towards the middle as we approach the number 7, which is neutral. These are going to be our weaker acids and bases. Concentration refers to the amount of acid or base in the solution. So you should recognize the term concentration from our work with Le Chatelier's principle. Remember that changing the concentration of something in a reversible reaction was one way to stress the system. So our concentration, as far as acids and bases go, refers to how much acid or base is in the solution. And we know this term concentrated. Concentrated means there's more of something, so more of the acid or base, or it could mean like higher purity of the acid or base. So if you're mixing with water, you're going to have much more of the acid or base than water. And dilute would mean less acid and base and more solvent. And I want to point out that this doesn't have to do with the strength of the acid or base. You could have a concentrated weak acid or a dilute strong acid. So it just depends on how much you're diluting it with your solvent. Acid-base reactions, hopefully you should know this, but when equal amounts of an acid or base are combined, then you're actually going to produce something neutral. So that should make sense because they balance each other out. And the neutral product that they're going to create is actually water. That's one of the products. And that's because our acid is giving up that hydrogen proton, the H+, and our base is giving up the hydroxide ion, the OH-, and combined together, those two things are going to share that electron that the OH has, and by sharing that, they're going to form a covalent bond, and they're going to form H2O. The other thing that they're going to form is going to be a salt, and that's going to be formed from whatever the other half of that acid and base was. So whatever those other elements or compounds are. So we've got two different examples here. We've got a sodium chloride, and we've got a sodium nitrate down here. So it's just going to be an ionic bond because we're going to have two different ions when our acid and our base split apart. And so we're going to form a salt by forming an ionic bond. And so both of these products, the salt and the water, are going to be neutral. So pH indicators are ways that we can measure the pH of a certain thing. So these are going to naturally change colors based on whether they're in contact with an acid or a base. And these are going to come from a variety of sources. We can make them synthetically, or they also actually occur naturally, which is pretty cool. So some examples of natural ones specifically are rose petals, turmeric, that's a spice, hydrangeas, red cabbage. We're going to be using red cabbage in our lab tomorrow, so that one you'll be familiar with. Lichens, beets, insects, spices, tea leaves, so a ton of different types of things here. And specifically the hydrangeas is pretty cool. You might have heard about this in biology class, maybe. But if you have hydrangeas on your lawn or somewhere, if you ever see hydrangeas, you can actually tell whether the soil underneath it and which they're grown in is more acidic or basic based on the color of those hydrangeas. So they're going to turn blue with more acidic types of soil, and they're going to turn pinker as they approach neutral and go into basic types of soil. And the next couple examples are just things that we might be using in class. Hoping on Thursday we're going to use some of these things. So I just want you to kind of understand how these specific pH indicators work. So litmus paper is a particular type of pH indicator, and in the presence of a base, if you dunk red litmus paper into a base, it's going to turn blue. And in the presence of an acid, blue litmus paper is going to turn red. So that's one way that we can use litmus paper to determine. We're also going to use phenolphthalein. So phenolphthalein just goes from colorless into like this kind of really nice deep pinkish red color. And in acidic solutions, your phenolphthalein is going to be colorless. And in more alkaline or basic solutions, your phenolphthalein is going to start to turn pink. So we're going to use that coming up this week. And our last one is going to be universal indicator. Universal indicator is super useful because it's a blend of multiple different pH indicators into one solution so that you can get this like very subtle gradation of different colors so that you can more easily pinpoint whether a solution is like a strong acid or a weak base or a strong base. Because if you notice, some of the other indicators are going to just give you kind of a basic distinction between acid and base. So in universal indicator, we've got these different colors. So we've got kind of a change from like this orangish red through yellow through green and then into like blue and purple. So this should get you started on the notes portion of things for today. And the only other thing that you have to do today is to read over the red cabbage lab that we're going to do tomorrow. I want you guys to be ready for that. And you're going to answer the pre-lab questions on the red cabbage lab. So those are on the last page of that lab. Hope you're having a good day.